In an X-ray image of Cassiopeia A, the dead star does not look like a single explosion anymore. It looks like a torn shell, a broken circle of hot gas and filaments expanding into the darkness, with colors assigned by instruments because human eyes could never see this kind of light directly. Silicon glows in one region, sulfur appears in another. Iron sits in knots and arcs that were once buried near the center of a massive star. Oxygen, calcium, argon, neon, and other elements have been pulled apart, heated, shocked, and spread into space. The image is not a painting of destruction, it is a map of chemistry made from X-rays, infrared light, spectroscopy, and years of careful observation. Somewhere inside that expanding remnant is the answer to a simple question that is not simple at all. How does the death of a star become the beginning of planets, oceans, rocks, atmospheres, and living cells? A supernova is often described as an explosion, and that is true, but it is also incomplete. It is a stellar ending that becomes a form of distribution. It takes material that has spent millions of years locked inside a star and throws it outward at thousands of kilometers per second. It sends shockwaves into surrounding gas. It seeds the interstellar medium with newly made elements. It leaves behind a neutron star, a black hole, or sometimes nothing recognizable as a star at all. Long after the first flash fades, the remnant remains, expanding, mixing, cooling, and becoming part of the galaxy again. A star dies, but the matter that made it does not vanish. It changes address. It enters clouds, it enters dust grains, it enters future systems that have not yet formed. If you could follow a single atom of oxygen in Cassiopeia A, you would not find a straight path from explosion to life. You would find turbulence, delay, collision, and chance. The atom might leave the star in a clump of hot ejecta. It might be heated by a reverse shock, slowed by magnetic fields, swept into a colder cloud, or locked into a tiny grain of silicate dust. It might wait in interstellar space for millions of years before gravity gathers the cloud around it into something denser. Then, if the conditions are right, it could become part of a protoplanetary disk around a new star. It might enter an icy planetesimal, a rocky mantle, a comet, or a molecule of water. This is not a single clean assembly line. It is a long physical chain, and every link is shaped by gravity, radiation, chemistry, and time. There is a piece of this story inside Earth itself. The iron in the planet's core did not form on Earth. The silicon in the rocks did not begin here. The calcium in bones, the phosphorus in DNA, the oxygen in water, and the carbon in living tissue all have histories older than the solar system. Some were made in ordinary stellar interiors before a star ever exploded. Some were made in the final burning stages of massive stars. Some were made in the explosive conditions of supernovae. Some of the heaviest elements may owe more to neutron star mergers than to ordinary supernovae, and that distinction matters. The universe does not make the periodic table in one place. It builds it through many kinds of stellar death, then mixes the results across galaxies. Supernovae are not only the bright deaths seen from a distance. They are part of the reason distance can contain anything familiar at all. A rocky planet requires heavy elements, what astronomers call metals, meaning nearly everything heavier than hydrogen and helium. A planet with a core, a crust, volcanoes, continents, minerals, and oceans cannot be made from the first simple gas of the universe alone. It needs previous generations of stars to have lived and died before it. The early universe had hydrogen, helium, and traces of lithium. It did not yet have enough iron for planetary cores, enough silicon for solid rock, enough oxygen for water, or enough carbon for organic chemistry. The first stars had to change that. If these long journeys through cosmic evidence are what bring you here, subscribing keeps the next one close. The first thing to understand is that not every star ends as a supernova. Our sun will not. It will swell into a red giant, shed its outer layers, and leave behind a white dwarf surrounded by a glowing planetary nebula. That ending is dramatic in its own way, but it is not the violent collapse of a massive star. Core collapse supernovae belong to stars born with far more mass than the Sun, roughly 8 solar masses or more, though the exact boundary depends on composition, mass loss, rotation, and binary interaction. These stars live fast because their gravity presses their cores to higher temperatures. They burn their fuel rapidly, step through nuclear stages quickly, and can reach an ending in only a few million years. A star 10 or 20 times the Sun's mass may look stable across human lifetimes, but inside it is changing continuously. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. In the most massive stars, later stages create neon, magnesium, silicon, sulfur, argon, calcium, and iron group nuclei. Each stage is shorter than the one before. Hydrogen burning may last millions of years. Helium burning may last hundreds of thousands. Carbon burning can last thousands. Silicon burning, near the end, may last only days. The star appears steady from outside because its surface hides the violence of the core. But deep within it, the available fuel is becoming more complex, more difficult to use, and less forgiving. Fusion works because light nuclei can combine into heavier nuclei and release energy, at least up to a point. That released energy helps support the star against gravity. Gravity tries to compress the star inward. Pressure from hot gas and radiation pushes outward. For most of a star's life, these forces stay close enough to balance that the star can shine for millions or billions of years. But the balance depends on energy production. When the core changes fuel, the star adjusts. It contracts, heats, ignites the next stage, and rearranges itself. In massive stars, this creates an internal structure often compared to an onion, with shells of different burning processes surrounding an iron-rich center. It is a useful image, as long as we remember that the real star is not calm or perfectly layered. It is turbulent, rotating, convecting, leaking mass, and interacting with its own radiation. Iron is where the ordinary logic of stellar fusion turns against the star. Fusing iron into heavier nuclei does not release energy in the way hydrogen fusion does. It requires energy. When a massive star builds an iron core, it has created material that can no longer serve as useful fuel for supporting the star. The core grows as surrounding shells continue to burn and deposit ash inward. It becomes denser, hotter, and more unstable. Electrons are forced into protons, producing neutrons and neutrinos. Photons break apart heavy nuclei, consuming energy that the core cannot spare. Pressure support weakens. Then, collapse begins. It is not a slow sinking, it is an inward fall of stellar material under gravity, with the central region reaching densities comparable to an atomic nucleus. The exact mechanism that turns collapse into explosion is still an active area of research. A simple description says the core collapses, rebounds, and drives a shock wave outward. That is part of the picture, but not enough by itself. In detailed models, the shock loses energy as it moves through the star, and neutrinos emitted from the newborn compact core appear to help revive it. Turbulence, convection, rotation, magnetic fields, and the structure of the star before collapse can all matter. This is why supernova simulations are difficult. They must follow gravity, nuclear physics, neutrino transport, fluid motion, and radiation in an object that is destroying itself. The final explosion is visible, but the engine is buried under layers of matter. The neutrinos are the first messengers from deep inside. In 1987, detectors on Earth recorded a brief burst of neutrinos from a supernova in the Large Magellanic Cloud before the optical light reached its full brightness. The event became known as Supernova 1987A, and it remains one of the most important stellar deaths ever observed. The neutrino detection confirmed that core collapse was happening in the heart of the star, hidden from direct view. The light that later brightened the southern sky came from the outer layers responding to that catastrophe. The neutrinos had escaped from deeper inside, almost as if the collapsing core had spoken before the star itself became visible. A core collapse supernova can release more energy in a short time than the Sun will emit across its entire main sequence life. Most of that energy is carried away by neutrinos, not visible light. The visible display, powerful as it is only a small surface expression of the deeper event. The star's outer layers are expelled. Shock waves move through gas that the star may have shed before it died. Radioactive isotopes decay and keep the remnant glowing. The expanding material slams into the surrounding interstellar medium, heating it to millions of degrees and producing X-rays. The remnant becomes a laboratory, but a difficult one, because everything is moving, cooling, ionizing, recombining, and mixing at the same time. The remnant left at the center depends on the mass and structure of the collapsing core. If the core settles into a neutron star, matter is packed so densely that a city-sized object can contain more mass than the Sun. If the collapse continues beyond what neutron degeneracy pressure and nuclear forces can support, a black hole forms instead. In some cases, material that initially escapes may fall back, changing the remnant. In others, the explosion may be weak or hidden. Astronomers do not always get a clean answer. A telescope image may show the expanding debris, while the central object remains obscured by dust, too faint, or simply not emitting in a wavelength that the available instruments can detect. SN 1987A showed how long the aftermath can remain scientifically alive. Decades after the light first reached Earth, telescopes were still watching its rings brighten as the blast waves struck material around the star. Infrared observations revealed dust. X-ray and radio observations traced shock interaction. More recently, Webb observations provided strong evidence for a neutron star hidden in the remnant, using signatures connected to ionized argon and sulfur. This is how modern astronomy often works. The explosion is not understood in a single night. It is followed across decades, across wavelengths, and across generations of instruments. A supernova becomes not one event, but a changing dataset. Cassiopeia A gives a different kind of view because it is older from our perspective, probably about 3.5 centuries past its explosion, and close enough in the Milky Way to be mapped in detail. Chandra observations show where elements such as silicon, sulfur, calcium, and iron emit X-rays. Webb sees infrared structures, knots of material, and dust features that reveal the remnant in another way. Hubble and ground-based observatories add optical and spectroscopic information. None of these images is the whole object. Each wavelength selects a different physical condition: hot plasma, cooler dust, shocked gas, synchrotron radiation, or specific ionized elements. Together, they let astronomers reconstruct the scattered interior of a dead star. The colors in these images are often assigned, not seen. That does not make them false. It makes them translated. X-rays have energies beyond what the human eye can detect. Infrared light carries information from dust and cooler material that would otherwise be invisible. Spectra reveal emission lines at particular wavelengths, and those lines correspond to atoms and ions. When an image shows iron in purple or sulfur in yellow, it is not claiming that the remnant would look that way through a window. It is showing a physical map. The color becomes a scientific label, a way of turning invisible radiation into something our visual brains can compare. Supernovae also come in more than one kind. A core collapse supernova is the death of a massive star whose core can no longer support itself. A Type 1a supernova is different. It involves a white dwarf, the compact remnant of a lower mass star, in a binary system. The white dwarf may draw material from a companion, or two white dwarfs may merge, or a helium layer may detonate and trigger deeper burning in some systems. In these events, runaway nuclear fusion can destroy the white dwarf. There may be no neutron star left behind. The star is not collapsing in the same way. It is being unbound by thermonuclear burning. Type 1a supernovae are especially important because many of them have similar intrinsic brightness after their light curves are standardized. This made them valuable distance indicators. By comparing their apparent brightness with their redshifts, astronomers discovered that cosmic expansion is accelerating, a result now described with the term dark energy. But Type 1a supernovae are not merely measuring tools, they are also chemical events. They produce large amounts of iron group elements and contribute to the enrichment of galaxies. The iron in planetary material is not from one kind of source alone. Core collapse supernovae and Type 1a supernovae both matter, but they contribute in different proportions and at different times in galactic history. The double detonation model for some Type 1a supernovae shows how much remains to be learned. In that scenario, helium gathered on a white dwarf's surface detonates first. The shock can then compress and ignite the carbon-oxygen core, causing a second detonation that destroys the star. Recent observations of some remnants have strengthened the case that this pathway really happens in nature. It is a reminder that the word supernova groups together events with different engines. To the eye, they may all be bright stellar explosions. To physics, they are not the same machine. Their light curves, spectra, remnants, and chemical yields carry clues about what actually happened. The brightness of a supernova can make the event seem sudden, but the preparation begins long before the flash. A massive star is born in a molecular cloud where cold gas and dust collapse under gravity. The cloud may be part of a spiral arm, a dense filament, or a region shaped by previous generations of stars. Young massive stars form in clusters because the same cloud often fragments into many objects at once. They shine intensely in ultraviolet light. They drive winds. They carve bubbles in the gas around them. Even before they explode, they are changing the environment that made them. Massive stars are rare compared with small red dwarfs, but their influence is disproportionate. A star with 20 or 30 times the mass of the Sun emits enormous amounts of radiation, loses material through powerful winds, and ends quickly. Its life may be measured in millions of years rather than billions. This means a massive star can die while its birth cluster is still young, while gas remains nearby, while other stars are still forming. The supernova does not explode into an empty stage. It explodes into a surrounding medium already sculpted by stellar winds, radiation pressure, and previous eruptions. The remnant we see later records that environment as well as the explosion itself. Before the final collapse, the star may have already shed a large fraction of its mass. Some massive stars become red supergiants, others become blue supergiants, or Wolf-Rayet stars, depending on mass, metallicity, rotation, and binary interaction. Many massive stars are not alone, and a companion can strip outer layers, transfer mass, or alter the final core structure. This is one reason supernova classification can be complicated. Spectra may show hydrogen, or lack it. They may show helium, or lack it. The light curve may rise and fade in ways that reveal interaction with surrounding material. Astronomers read these differences like forensic clues, not because the universe labels its explosions, but because atoms leave signatures. Inside a massive star near the end, time becomes compressed. The outer layers may be immense, perhaps hundreds or more times the radius of the Sun, while the core moves through its final stages at an accelerating pace. Silicon burning can build iron group nuclei in a period so short that an observer outside the star would not know anything visible had changed. The surface still shines. The star still occupies its place in the sky. But the center is approaching a limit. The star has spent its life delaying gravity by fusion. Now the last fuel capable of useful support is gone. The end is no longer a distant fate. It is a mechanical consequence. When collapse begins, the core falls inward at a significant fraction of the speed of light. Electrons and protons combine into neutrons, and neutrinos flood out. The inner core stiffens when nuclear densities are reached, while outer material continues falling. A shockwave forms, stalls, and may be revived. If the explosion succeeds, the star is ripped apart from within. If it fails, much of the star may fall inward, and a black hole may form with little visible display, or with a different kind of transient. The word death is useful, but it can make the process seem biological. It is not. It is pressure, gravity, quantum mechanics, nuclear binding energy, and hydrodynamics meeting a limit. Some of what we know about supernova interiors comes from the material they eject. If a remnant contains oxygen-rich knots, silicon-rich layers, and iron outside where simple models would not place it, then the explosion must have mixed the star. If a neutron star is moving away from the center, then asymmetries may have kicked it during the event. If radioactive isotopes are found in particular patterns, they point to burning conditions that existed only briefly. Astronomers cannot place instruments inside a dying star, but the explosion opens the star after the fact. It scatters the evidence in space, and the remnant becomes a kind of three-dimensional autopsy. The elements released by supernovae are not all made at the same moment. Carbon and oxygen can be made during normal stellar burning before the explosion. Silicon, sulfur, argon, calcium, and iron group elements can be made in late burning stages or during explosive burning as the shock passes through layers of the star. Type 1a supernovae are major producers of iron group material. Some neutron-rich isotopes require environments with intense neutron flows. For decades, core collapse supernovae were often treated as the main R process factories. But observations of neutron star mergers have shown that mergers are very important for many of the heaviest elements, including gold and platinum. Supernovae still matter enormously, but the full chemical story is shared. This matters because a phrase like star stuff can hide complexity. It is true that humans are made of elements forged in cosmic processes, but those processes are not one furnace. Hydrogen in your body largely comes from the Big Bang. Carbon may come from aging stars and massive star winds as well as supernova-related environments. Oxygen is heavily associated with massive stars. Iron has major contributions from both core collapse and Type 1a supernovae. Some iodine, gold, and other heavy elements may trace neutron star mergers. The periodic table is a record of many deaths, many collisions, and many long cycles of mixing. A living cell is chemically local, but historically galactic. The path from a supernova to a planet begins with enrichment. The explosion expands into the interstellar medium, which is not a perfect vacuum. It contains thin gas, dust grains, magnetic fields, cosmic rays, and older material from other stars. The blast wave sweeps up gas and compresses it. The ejecta mix with surrounding matter, though not instantly and not perfectly. Some newly formed dust survives. Some is destroyed by shocks. Some atoms remain in hot plasma for a long time before cooling. Over time, turbulence in the galaxy stirs the material into larger reservoirs of gas. The chemistry of a future star-forming cloud is never the product of one supernova alone, but of many sources blended unevenly. A molecular cloud can contain material from thousands or millions of previous stars, depending on its history and location in the galaxy. It is cold by astronomical standards, often only tens of degrees above absolute zero in dense regions, and filled with molecules such as hydrogen, carbon monoxide, water ice, ammonia, and more complex compounds on dust grains. Gravity does not always win in such clouds. Turbulence, magnetic fields, and radiation can support or disrupt them, but in some regions, dense cores collapse. A new star forms at the center. Around it, a rotating disk becomes the construction site for planets, moons, asteroids, comets, and the leftover debris of a young system. The solar system formed about 4.6 billion years ago from such a cloud. The material that became the Sun, Earth, meteorites, and every planet was already enriched. It contained iron, silicon, magnesium, oxygen, carbon, nitrogen, sulfur, calcium, aluminum, nickel, and many other elements that could not have existed in large quantities in the early universe. Meteorites preserve clues from that time. Some contain calcium-aluminum-rich inclusions, among the oldest known solids in the solar system. Some isotopic patterns suggest that short-lived radioactive nuclei, such as aluminum-26 and iron-60, were present early on. The origin of those isotopes is studied carefully, and nearby massive stars or supernova input may have played a role. It is tempting to say that one supernova directly triggered the birth of the Sun, but the evidence is not that simple. Some models allow a nearby supernova shock to inject material into a collapsing cloud or help compress it. Other models involve winds from massive stars, earlier enrichment over longer times, or a complex star-forming region where many sources contributed. Meteorite isotopes are real evidence, but interpretation depends on models of mixing, timing, and nucleosynthesis. The safer statement is also more interesting. The solar system formed in an environment already shaped by massive stars, and at least some of its early radioactive inventory likely points back to stellar sources that lived and died before the Sun. Once the protoplanetary disk formed, heavy elements changed everything. Hydrogen and helium dominated the mass of the Sun, but solids in the disk were made from the rarer ingredients. Close to the young Sun, heat kept water and many volatile compounds from condensing easily, while refractory minerals survived. Farther out, ices could form. Dust grains collided and stuck. Pebbles became planetesimals. Planetesimals became planetary embryos. Gravity amplified the differences. Iron and nickel sank toward the centers of growing rocky bodies, forming metallic cores. Silicate minerals built mantles and crusts. Volatile rich material delivered water and carbon-bearing compounds in ways still being studied. Without previous stellar enrichment, there would be no Mercury, Venus, Earth, or Mars as rocky worlds. There would be no iron core to help power Earth's magnetic field, no silicate mantle for plate tectonics, no uranium, thorium, and potassium to contribute to internal heat over geological time. No calcium carbonate shells, no phosphorus backbone for DNA, no oxygen-rich minerals, no carbon chemistry in the form life uses. Hydrogen alone can make stars. Hydrogen and helium can make gas giants. But a living rocky planet requires a much broader inventory. Supernovae are not the only sources of that inventory, but they are among the central reasons it exists. Look at a meteorite slice in a laboratory. It does not glow like a supernova remnant. It is quiet, dark, metallic, sometimes speckled with chondrules and inclusions. Under a microscope, it becomes a record of heat, cooling, collision, and chemical separation in the early solar system. In its isotopes, it can also carry older memories. Some pre-solar grains found in meteorites formed around other stars before the Sun existed. They survived interstellar space, survived the collapse of the solar nebula, and were trapped in primitive material. A grain smaller than dust can contain evidence of a star that died before Earth formed. That is not metaphor. It is laboratory measurement. The story of supernovae creating planets is therefore not a story of a single blast throwing ready-made worlds into space. It is a slower and more physical story. Stars make elements. Explosions and winds eject them. Galaxies mix them. Clouds cool and collapse. Disks form. Dust becomes solids. Solids become worlds. Some worlds retain atmospheres. Some gather oceans. Some become sterile, some unstable, some frozen, some scorched. One planet, at least, developed chemistry complicated enough to become biology. The supernova is not the whole cause of life. It is one of the conditions that made the chemical stage possible. Supernovae also destroy. A nearby explosion can flood space with high-energy radiation and cosmic rays. If close enough to a life-bearing planet, it could damage atmospheres, alter ozone chemistry, increase radiation at the surface, and affect ecosystems. The danger depends on distance, explosion type, magnetic fields, interstellar environment, and planetary protection. Earth has almost certainly been exposed to nearby supernova debris in the past. and traces of iron-60 in ocean sediments and crusts have been studied as possible evidence of relatively recent nearby events in geological terms. These were not the explosions that made Earth, but they show that stellar death can leave fingerprints even on a planet already formed. The Milky Way probably experiences supernovae at a rate of a few per century, but most are hidden from direct naked-eye view by dust or occur on the far side of the galaxy. Human history records only a handful clearly, such as the supernova of 1054 that produced the Crab Nebula, Tycho's supernova in 1572, and Kepler's supernova in 1604. These events were bright enough to be noticed before modern telescopes, and they later became objects of detailed scientific study. The Crab Nebula now reveals a pulsar at its center, spinning rapidly and powering the surrounding nebula. What ancient observers saw as a new star was the visible surface of a core collapse remnant still active almost 1,000 years later. A pulsar is one of the possible afterlives of a massive star. It is a rotating neutron star with strong magnetic fields, sending beams of radiation into space. If those beams cross Earth, detectors register pulses with extraordinary regularity. The Crab pulsar rotates about 30 times per second, slowing gradually as it loses energy. That energy feeds the nebula around it. In images, the Crab is not simply a cloud left behind by an explosion. It is a system, a compact object, magnetic fields, relativistic particles, expanding debris, and radiation across the spectrum. The supernova did not just scatter elements. It created an engine. Not all remnants have a visible pulsar. Some central neutron stars are faint. Some may have magnetic fields or orientations that make pulses hard to detect from Earth. Some remnants may contain black holes. Others are thermonuclear Type 1a remnants with no compact core at all. This diversity matters because each remnant is a clue to the explosion that made it. A shell-like remnant expanding into uniform gas tells one story. A remnant crashing into dense knots of circumstellar material tells another. A remnant rich in oxygen points to massive star layers. A remnant dominated by iron group material may suggest a Type 1a origin. Astronomers compare morphology, spectra, expansion speeds, and chemical maps to models, then revise the models when the sky refuses to be simple. Even the word remnant can understate what is happening. The material is not passive debris. The forward shock moves into the surrounding interstellar gas. A reverse shock travels back into the ejecta, heating material that was once expanding freely. Electrons spiral in magnetic fields and produce synchrotron radiation. Dust grains are sputtered, shattered, or heated until they glow in infrared light. Atoms are ionized and then recombine. Cosmic rays may be accelerated at shock fronts. A supernova remnant is an evolving plasma environment, and its appearance changes with time. To understand it, astronomers need images separated by years, spectra across wavelengths, and models of how shocks behave. Spectroscopy is one of the main tools. When light from a remnant is spread into a spectrum, emission lines appear at specific wavelengths. Oxygen has its signatures. Hydrogen has its signatures. Sulfur, iron, calcium, argon, and neon each leave different marks. If those lines are shifted, astronomers can measure motion through the Doppler effect. Material moving toward us shifts one way. Material moving away shifts another. In some nearby remnants, this allows three-dimensional reconstruction. The object on the screen becomes not merely a flat shell but an expanding structure in space, with clumps moving at different velocities. The remnant is a record of the explosion's asymmetry. That asymmetry is important. For a long time, simple diagrams made supernovae look like smooth spheres. Real supernovae are messier. Instabilities grow as shocks pass through layers of different density. Plumes of nickel and iron can push outward. Oxygen-rich knots can move in unexpected directions. Neutron stars can receive kicks that send them racing away from the original center. The explosion of a massive star is not a perfect fireball. It is a gravitational collapse trying to reverse itself through turbulence, neutrino heating, and fluid motion. The irregular structures seen in remnants are not imperfections in the data. They are evidence of the physical violence inside the star. There is something almost understated about the way a spectrum tells this story. No flames, no sound, no human-scale blast wave, just peaks and lines on a detector. A line at one energy means silicon. Another means iron. A broadened line means fast motion. A faint line means a small amount of material, or material at the wrong temperature, or material hidden by absorption. Scientists compare these lines to laboratory measurements and atomic databases. The evidence is not dramatic in its raw form. It is numbers, counts, wavelengths, uncertainties, and calibration files. But through those numbers, the interior of a dead star becomes readable. In Cassiopeia A, Chandra observations have estimated large amounts of oxygen, silicon, sulfur, calcium, and iron in the remnant. These are not decorative details. Oxygen is the most abundant element in Earth's crust by mass. Silicon is central to rock. Iron dominates Earth's core. Calcium enters minerals and living skeletons. Sulfur participates in geology and biology. When astronomers map these elements in supernova debris, they are watching the raw ingredients of rocky planets before they become rocks. The remnant is not a planet factory by itself, but it supplies material that future planet-forming systems can use once the galaxy has mixed, cooled, and reorganized it. Dust is one of the uncertain links. Supernovae can form dust in their cooling ejecta, and observations of remnants such as SN 1987A suggest large amounts of dust can exist after an explosion. But shocks can also destroy dust. The question is how much survives long enough to enter the interstellar medium and contribute to later clouds. This is not only a detail for specialists. Dust grains are where molecules form, where light is absorbed and re-emitted, where protoplanetary disks begin their solid inventory. A galaxy's dust content affects star formation, chemistry, and planet formation. Whether supernovae are major dust sources, dust destroyers, or both depends on environment and time. Webb's infrared view is especially useful here because dust that hides visible light can glow or become more transparent at longer wavelengths. In SN 1987A, the debris that concealed the central compact object for decades could be probed with infrared instruments. In Cassiopeia A, Webb shows filaments, knots, and structures with a level of detail that helps connect dust, ejecta, and shock interaction. These images are beautiful, but their beauty is not separate from the measurement. Each structure is an energy balance, a density contrast, a temperature, an ionization state, and a history of motion through space. The galaxy itself keeps the process from ending at the remnant boundary. The Milky Way rotates. Spiral arms compress gas. Superbubbles blown by clusters of massive stars expand and merge. Hot gas rises into the halo and may cool back down. Molecular clouds are built and destroyed. Elements made in one region can be carried elsewhere over long times. This circulation is called galactic chemical evolution, and it explains why later generations of stars tend to contain more heavy elements than earlier ones. Astronomers can see this in stellar populations. Old halo stars are often metal-poor. Younger disk stars can be more enriched. The chemical abundance of a star is partly a timestamp. Planet formation depends strongly on this enrichment. A protoplanetary disk around a star with almost no heavy elements cannot build rocky planets efficiently because there are too few solids. In the early universe, before enough stars had died, the first planets must have been rare or different. As galaxies aged and metal content increased, the raw material for terrestrial planets became more available. This does not mean every enriched star has an Earth. Far from it. Disk mass, stellar radiation, orbital dynamics, impacts, migration, water delivery, and chance all matter. But supernovae and other stellar deaths changed the probability space. They made solid worlds chemically possible. Imagine a young galaxy before much enrichment. It has stars, gas, gravity, radiation, and perhaps massive clusters blazing in blue-white light. But its chemistry is still simple compared with the Milky Way today. Then, generations pass. Massive stars explode, white dwarfs detonate, aging stars shed carbon-rich winds, neutron stars merge in rare but powerful events. Each process adds something. The interstellar medium becomes less primordial. Cooling becomes more efficient because heavy elements radiate energy through spectral lines. Dust becomes more common. Star formation changes. Planets become easier to build. Life, if it emerges, does so only after the universe has had time to become chemically complicated. This is why the age of the universe matters to the story of life. The universe is about 13.8 billion years old. Earth is about 4.5 billion years old. The Sun did not form at the beginning. It formed after billions of years of earlier stellar history had already enriched the Milky Way. We live around a second or later generation star, not in the first chemical dawn. The atoms in Earth were not assembled in a single ancestral star, but in many. The solar nebula was a mixture. Some material was ancient. Some may have arrived from relatively recent nearby massive star activity. Some had been cycling through the galaxy for a long time before it entered the cloud that became the Sun. Astronomers use abundance ratios to trace these histories. Oxygen relative to iron, magnesium relative to silicon, europium relative to iron, carbon relative to nitrogen. Each ratio can reveal something about the sources that enriched a gas cloud. Core collapse supernovae occur quickly after massive stars form, so they enrich galaxies early with alpha elements like oxygen and magnesium. Type 1a supernovae often occur after longer delays, adding iron over extended times. Neutron star mergers may have their own delay times and yields. When scientists measure old stars, globular clusters, dwarf galaxies, or the Milky Way disk, they are not only cataloging composition, they are reconstructing the timing of stellar death. This reconstruction is imperfect. Stars migrate through galaxies. Gas flows in and out. Dwarf galaxies merge with larger ones. Some supernova yields depend on the progenitor's mass, metallicity, rotation, and explosion energy. Type 1a progenitor channels are still debated. Neutron star merger rates and early R process enrichment remain active research topics. A chemical abundance pattern can point strongly toward a source, but it does not always produce a single unambiguous answer. The galaxy is a stirred, evolving system, not a sealed experiment. Scientific caution is not weakness here. It is the only way to keep the story honest. One of the most direct ways to study supernova creation of elements is to watch a supernova while it is still bright. In the first days and weeks, spectra show the outer layers expanding. Later, as the ejecta thin, deeper material becomes visible. Radioactive nickel decays into cobalt and then iron, helping power the light curve. Gamma rays and optical lines reveal where radioactive material went. If the light curve fades too quickly or too slowly, if certain lines appear or fail to appear, if velocities are high or low, the explosion model must account for it. A supernova is a clock, a lamp, and a chemical sample at once, but only if observed carefully. Modern surveys catch thousands of supernovae because robotic telescopes repeatedly image large areas of sky and compare new frames with old ones. A point of light appears where there was none before. Software flags it. Astronomers follow up with spectroscopy. The supernova receives a designation, and its brightness is monitored as it rises and fades. Some are nearby and detailed, some are distant and faint, some are ordinary, some are strange. Behind every catalog entry is a star or compact object undergoing an irreversible event. The database grows because the sky is watched systematically, not because the universe waits for humans to notice. At cosmological distances, supernovae become messages from earlier epochs. Their light may travel for billions of years before entering a telescope. The explosion itself is long over by the time it is observed. Its remnant may have already faded, mixed, and entered other clouds in its own galaxy. But the light curve arriving now still carries the physics of the event. Type 1a supernovae, in particular, have allowed astronomers to measure cosmic distances across enormous scales. The same kind of explosion that helps make iron for planets also helped reveal that the expansion of the universe is accelerating. A stellar death became a tool for discovering something about the fate of cosmic space. Yet the supernova that matters most for life is not necessarily the brightest or most distant. It is the one whose material actually enters a later star-forming region. Most ejecta do not go directly into living chemistry. Much of it spends long periods diluted in hot gas. Some may leave a galaxy in outflows. Some may remain in a halo. Some may be incorporated into stars that never form planets. Some may enter gas giants or asteroids or worlds where chemistry never becomes biology. The link between supernova and life is real, but it is statistical, cumulative, and indirect. It is not destiny. It is possibility created by material availability. On Earth, that possibility became physical. Iron sank into the core, helping shape the planet's magnetic and thermal history. Silicates formed a mantle and crust. Volcanism released gases. Impacts delivered and redistributed volatiles. Water collected on the surface. Carbon moved between atmosphere, ocean, rock, and life. Phosphorus entered minerals and biological molecules. Calcium entered shells and bones much later, after life had already evolved and changed the planet. The elements did not guarantee any of this. They allowed it. A planet is not alive because it contains carbon. But without carbon, oxygen, nitrogen, phosphorus, sulfur, iron, and trace metals, life as we know it has no chemical language. The role of iron is especially direct. In Earth's core, iron alloyed with nickel and lighter elements forms a metallic center. Motion in the liquid outer core helps generate the magnetic field. In biology, iron appears in hemoglobin, in enzymes, and in electron transfer systems. But iron is not easy for stars to make in ordinary, energy-releasing fusion beyond a certain point. It is produced in large quantities through the late stages and explosions of stars, especially Type 1a supernovae for much of the galactic inventory. The iron in blood and the iron in a supernova remnant are not poetically connected. They are chemically connected by nuclear history. Oxygen tells a different but equally important story. It is made efficiently in massive stars and released through their winds and explosions. It becomes part of silicate rocks, water molecules, carbon dioxide, and the atmosphere after biological processes transform a planet. In Cassiopeia A, oxygen-rich material is visible as part of the remnant's expanding debris. In Earth's crust, oxygen is bound into minerals under your feet. In a molecule of water, it participates in a solvent that makes biological chemistry possible. The same element can be plasma in a remnant, ice in a comet, mineral in a mantle, and liquid in an ocean. The atom is not changed by our categories. Carbon is more complicated because much of it is made and distributed by stars that do not explode as core collapse supernovae. Low and intermediate mass stars can produce carbon and release it through stellar winds during their giant phases. Massive stars also contribute. Supernovae can both create and disperse carbon-bearing material, and their shocks can alter carbon chemistry in surrounding clouds. The carbon in life, therefore, comes from a broader stellar ecology. It is not accurate to assign it to supernovae alone. But supernovae help keep the interstellar medium dynamic and enriched, and they participate in the chain that makes carbon-bearing planets possible. Nitrogen, phosphorus, sulfur, and trace metals each have their own histories. Nitrogen can be produced in stars through cycles involving carbon and oxygen. Phosphorus is less abundant but biologically crucial, and its cosmic origins involve massive stars and explosive environments that are still studied. Sulfur is produced in massive star burning and supernova processes and appears in both minerals and proteins. Copper, zinc, molybdenum, and other trace elements matter to enzymes even in tiny amounts. Life uses the periodic table unevenly, but it uses more than the simplest elements. The existence of those options reflects billions of years of nucleosynthesis before Earth ever cooled. A supernova is therefore an event where scale changes violently. The core is small compared with the star, yet controls the ending. The explosion lasts days to months in light, yet its chemical consequences last billions of years. The remnant may span light years, while the dust grains that form inside it are microscopic. The material may become part of a cloud hundreds of light years across, then part of a disk smaller than a light year, then a planet, then a cell. Physics connects those scales without needing them to feel connected. Gravity, pressure, radiation, shocks, and chemistry carry the story from stellar interiors to planetary surfaces. The distance to these objects also changes how we know them. Cassiopeia A is about 11,000 light-years away. SN 1987A is about 160,000 light-years away in the Large Magellanic Cloud. The Crab Nebula is roughly 6,500 light-years away. These distances mean we are looking at delayed light. The events happened before the light reached us. The remnant we see is a combination of physical age and light travel time. Astronomers account for this, but the emotional fact remains strange. A telescope image can show a relatively young remnant, while the explosion itself occurred long before anyone built the detector that now records it. The images arrive as data, not as sound. Space does not carry the blast to us through air. The detector counts photons, a mirror gathers them, a sensor converts them into signals, a computer stores them. Calibration removes instrumental effects. Scientists compare exposures, spectra, and models. The public image may come later, processed so structures can be seen. What looks like a glowing cosmic object on a screen is the end of a long chain of collection and interpretation. The supernova itself was physical. Our knowledge of it is mediated by instruments, mathematics, and patience. Sometimes the evidence is a single new point in a galaxy. A survey image from one night is subtracted from an older reference image. Most stars disappear because they were present in both. What remains is a transient, a small bright difference that was not there before. That difference may be a supernova. Follow-up observations begin. The spectrum shows broad lines. Because material is moving fast, the light curve rises, the classification becomes clearer, the object is added to a global network of alerts. Somewhere in another galaxy, a star has died, and on Earth it first appears as a pixel that failed to match its past. The expanding debris can move at tens of thousands of kilometers per second, but it does not expand forever unchanged. As it sweeps up surrounding material, it slows. Energy moves into shocks, heat, radiation, and accelerated particles. Eventually, over tens of thousands or hundreds of thousands of years, the remnant fades into the interstellar medium. By then, the distinct shell may no longer be visible. The elements have not disappeared. They have become part of a larger reservoir. This fading is essential. A remnant that stayed isolated forever would not enrich future stars effectively. Mixing is less spectacular than explosion, but it is just as important for planets. The interstellar medium has phases: cold molecular gas, warmer neutral gas, ionized regions around hot stars, and extremely hot plasma in bubbles and remnants. Supernovae help maintain this structure. They inject energy and momentum. They can compress gas in some places and disperse it in others. They may trigger star formation under certain conditions, but they can also prevent it by heating and stirring gas too strongly. The relationship is not simple. A shock wave moving into a dense cloud edge may help collapse a core. A shock moving through a smaller cloud may shred it. Supernova feedback is both creative and disruptive, depending on scale and environment. This is one place where popular descriptions often become too neat. A supernova does not automatically create new stars wherever it passes. It does not automatically destroy every cloud either. The outcome depends on density, magnetic fields, shock speed, cooling, geometry, and timing. In simulations, feedback from massive stars is needed to reproduce realistic galaxies, because without it, gas can collapse too efficiently into stars. But the details remain difficult. The same phenomenon that supplies heavy elements also regulates how quickly galaxies turn gas into stars. Stellar death shapes the future population of stars, not only by enrichment, but by controlling the gas from which those stars form. In a star-forming region, generations can overlap. Massive stars born first may explode, while lower mass stars from the same complex are still young. Their shockwaves may move through gas that has already been carved by radiation. New stars may form in compressed ridges. Other gas may be blown away, ending local star formation. The cluster disperses. Some stars drift into the galaxy. Planets form or fail around them. Millions of years later, the massive stars are gone, but their influence remains in the motions, abundances, and architecture of the region. The sky does not preserve the event as a simple marker. It preserves consequences. We can see large-scale consequences in superbubbles, enormous cavities inflated by winds and supernovae from groups of massive stars. The local bubble, the low-density region around the Sun, is thought to have been shaped by past supernovae and stellar winds. This means the solar system moves through an interstellar environment influenced by previous stellar deaths. Nearby supernovae may also have deposited iron-60 on Earth within the last few million years, according to studies of deep ocean crusts and sediments. These traces are faint compared with the original explosions, but they show that supernova material can cross interstellar distances and arrive at a planet as measurable atoms. The thought is quiet in the laboratory. A sample is cleaned. Atoms are counted with specialized instruments. A rare isotope appears in a layer whose age can be estimated. The number is tiny, almost absurdly small compared with the mass of Earth, but it is not nothing. It may be debris from a star that died close enough for its dust to reach the solar system. The supernova was not seen by humans if it happened millions of years ago. No historical record exists. But the ocean floor may have kept a trace, a geological echo of an astrophysical event. If a supernova happened too close today, the concern would not be the blast wave reaching Earth like an explosion in air. The distances are too large for that kind of simple picture. The concern would be radiation, cosmic rays, and atmospheric chemistry over time. A very nearby event could damage the ozone layer and increase harmful ultraviolet radiation at the surface. It could alter climate or biology, depending on distance and exposure. But no known star is currently positioned to produce an imminent supernova threat to Earth. Betelgeuse, for example, will explode someday in astronomical terms, but current evidence does not place that event on a human schedule, and it is far enough away not to threaten Earth. When Betelgeuse does eventually explode, it will be a remarkable sight if humans or other observers are here. It may become very bright in Earth's sky, perhaps visible in daylight for a time depending on the details. But the scientific value would be even greater than the spectacle. Detectors would look for neutrinos. Telescopes across the spectrum would monitor the rise, peak, and decline. Gravitational wave instruments might search for signals if the asymmetry and distance allowed. Astronomers would already have pre-explosion data on the star, making it possible to connect its prior behavior with its death. A nearby supernova would become the best observed stellar collapse in history. Yet predicting the exact moment of a massive star's explosion is extremely difficult. Stars can vary, shed material, dim, brighten, pulsate, and produce unusual signals without being at the final moment. Betelgeuse's recent dimming attracted attention, but it was not a countdown. Dust, surface activity, and pulsation can change a red supergiant's brightness. The final silicon burning stage is hidden deep inside. Unless neutrino detectors catch the last warning from the core, the outside of the star may not clearly reveal that collapse is hours or days away. The star keeps its secret until physics no longer allows it to do so. Neutrino early warning systems exist because neutrinos can escape from a collapsing core before light escapes the outer layers. If a galactic supernova occurred, detectors around Earth could register a burst and alert astronomers to look for the optical event. This would be a reversal of ordinary astronomy. Instead of seeing light first and inferring the hidden core, scientists might detect the core collapse first and wait for the star to brighten. The event would connect particle physics, stellar evolution, high-energy astrophysics, and observational astronomy in real time. It would also test models that have been refined for decades, mostly against distant or older remnants. Gravitational waves may also carry information from core collapse if the explosion is asymmetric enough and close enough. These ripples in space-time would not come from the expanding shell in the way light does, but from rapid mass motion in the collapsing core. Detecting them from a supernova would be difficult, but valuable. Combined with neutrinos and electromagnetic radiation, they would create multi-messenger astronomy of stellar death. Each messenger escapes different regions and responds to different physics. Light shows the outer layers and radioactive aftermath. Neutrinos reveal the dense core. Gravitational waves could show the dynamics of collapse. Together, they would make the hidden engine less hidden. This is the direction modern astronomy has been moving, from images alone to layered evidence. A supernova is no longer only a bright point that appears and fades. It is a neutrino source, a gravitational possibility, a chemical factory, a dust laboratory, a shock accelerator, a distance marker, a remnant, and a contributor to planetary material. Each role is real, but none is complete by itself. The danger is to reduce the event to one image, one metaphor, one answer. The better approach is slower. Watch the star before it dies if possible. Record the explosion. Map the remnant. Measure the elements. Follow the material into the galaxy. The Crab Nebula demonstrates how a historical supernova can become a modern physics laboratory. Chinese and other observers recorded a guest star in 1054. Today, telescopes see an expanding nebula powered by a pulsar. The pulsar's magnetic field and rotation accelerate particles to high energies. The nebula shines from radio waves to gamma rays. Filaments contain gas moving outward from the explosion. The system is young enough to connect with historical records and old enough to show how a compact remnant energizes its surroundings. It is not just a fossil, it is still active, converting rotational energy into radiation and particle motion. Kepler's supernova remnant tells another story. Observed in 1604, it was the last supernova in the Milky Way, clearly visible to the naked eye. Modern observations suggest it was a Type Ia event, the thermonuclear destruction of a white dwarf. Though its surrounding environment has complexities. The remnant is studied in X-rays, optical light, and infrared, each wavelength revealing different material. The historical record says a new star appeared. The modern record says a compact stellar remnant was destroyed, heavy elements were expelled, and a shock continues to expand through gas. 4 centuries separate the human observation from the physical analysis, but they refer to the same event. Tycho's supernova of 1572 is similarly important. It challenged the old idea that the heavens were unchanging because a bright new object appeared in a sky that was supposed to be fixed. Today, the remnant is understood as another Type Ia supernova, with an expanding shell visible in X-rays and radio. The philosophical consequence in the 16th century was that the sky could change. The scientific consequence now is that the remnant can be compared with models of white dwarf explosions. The same object belongs to the history of ideas and to the physics of nucleosynthesis. It changed human understanding, but it was never about humans first. It was a star system reaching its limit. Supernova names can make them feel like catalog entries, but each one is a particular event in a particular environment. SN 1987A was a blue supergiant, not the red supergiant many expected for that kind of explosion. Cassiopeia A may involve complex pre-supernova mass loss and asymmetry. Some supernovae interact strongly with dense material around the star, producing bright emission lines and long-lasting light. Some are stripped envelope events, where hydrogen and helium layers were removed before explosion. Some are unusually luminous and may involve magnetars or extreme circumstellar interaction. Some are faint, failed, or difficult to classify. The diversity is not noise around the main story, it is the main story becoming more accurate. Because of that diversity, it is better to say supernovae help create and distribute many elements necessary for planets and life, not that every atom in life came from one supernova. The title of this journey is true in the broad sense, but the details matter. Dying stars create elements through fusion and explosive nucleosynthesis. Supernovae eject them into the galaxy. Those elements become part of later star and planet formation. Life uses some of them. But the chain includes other stellar sources, long mixing times, disk chemistry, planetary geology, and biological evolution. The universe does not hand over finished worlds. It supplies ingredients and physical conditions. The first generation of stars, often called population the 3 stars, would have formed from almost pristine hydrogen and helium. None has been directly observed in its original form, but theory suggests many were massive and short-lived. Their deaths would have begun enriching the universe with heavier elements. After that, star formation changed because gas-containing metals can cool differently. The earliest supernovae may have helped transform the universe from a simple chemical state into one capable of making dust, small stars, and eventually planets. This happened long before Earth, before the Sun, before the Milky Way had its present structure. The origin of life on Earth is local, but its chemical prehistory reaches back into cosmic dawn. Redshift lets telescopes look into that earlier history. A distant galaxy is seen as it was when the universe was younger. Its spectrum can reveal heavy elements already present. Quasars shining through intervening gas show absorption lines from carbon, oxygen, silicon, and other elements in the early universe. These observations tell astronomers that enrichment began quickly. Massive stars can live only a few million years, so their supernovae can pollute surrounding gas early. The earliest planets, if they existed, may have formed under conditions very different from the solar system. The full timeline from first stars to first habitable worlds is still uncertain, but it depends on how quickly stellar death complicated the chemistry of galaxies. In the Milky Way today, we can see enrichment in star-forming regions such as Orion, Carina, and other nebulae. Massive stars illuminate gas, carve cavities, and will eventually explode if they are massive enough. Around younger stars, disks contain dust that may become planets. These regions are not isolated from galactic history. Their gas has been processed by earlier stars. When a telescope observes a protoplanetary disk, it is seeing the next stage of a cycle that includes old supernovae, stellar winds, cloud collapse, and disk evolution. The disk may look delicate in an image, a thin dark lane or bright ring, but chemically, it carries the memory of violent events. A protoplanetary disk does not know the supernova that enriched it. It follows local physics. Gas orbits the young star. Dust settles toward the midplane. Ice lines mark temperature zones. Turbulence stirs particles. Magnetic fields and radiation affect the gas. Planetesimals grow by collision and concentration. The heavy elements are simply present, available for construction. Their origin is no longer visible in the disk's shape, but without them, the disk would be mostly gas, unable to build the rocky architecture that later becomes planets, moons, asteroids, and meteorites. Exoplanet studies show that planet formation is common, but not uniform. Transit light curves reveal planets crossing in front of stars. Radial velocity measurements show stars wobbling under planetary gravity. Direct imaging finds young giant planets far from their stars in some systems. Spectroscopy begins to probe atmospheres. Across thousands of confirmed exoplanets, astronomers see hot Jupiters, super-Earths, mini-Neptunes, compact multi-planet systems, eccentric giants, and worlds unlike anything in our solar system. Heavy element enrichment is one ingredient among many. It helps build solids, but orbital architecture depends on disk evolution, migration, collisions, and timing. The fact that planets are common does not make Earth inevitable. The solar system has its own history: the growth of Jupiter and Saturn, the scattering of small bodies, the late delivery of volatiles, the moon-forming impact, the stabilization of Earth's rotation, the evolution of atmosphere and oceans, and the long biological transformation of the surface. Supernovae supplied some of the ingredients, but the recipe unfolded through planetary dynamics and chemistry. A galaxy can be rich in heavy elements and still produce countless sterile worlds. The connection between supernovae and life is therefore not a guarantee. It is an enabling condition spread across deep time. This distinction protects the wonder rather than reducing it. If supernovae automatically created life, the story would be simpler and less true. Instead, they create the possibility of complex chemistry. They make planets with cores, mantles, crusts, and trace elements possible. They enrich the clouds from which stars form. They drive shocks that can reshape star-forming environments. But after that, many other filters remain. The planet must form in a suitable environment. It must retain or acquire the right volatiles. It must avoid sterilizing histories or recover from them. Chemistry must cross thresholds that are still not fully understood. Life is connected to supernovae, but not explained by them alone. Still, the connection is profound because it means life is not chemically separate from the galaxy. The atoms in biology are not special exemptions from cosmic history. They are ordinary atoms with extraordinary arrangements. Carbon, bonds, oxygen chemistry, iron redox reactions, phosphorus chains, sulfur bridges, magnesium in chlorophyll, calcium in signaling and skeletons, each depends on elements built or distributed by stellar processes. A cell is small enough to be seen under a microscope. Its elemental ancestry includes stars massive enough to collapse, binary remnants dense enough to detonate, and galactic clouds large enough to form clusters. Scale does not break the connection. The evidence for this connection is not only philosophical. It comes from nuclear physics, meteorite isotopes, stellar spectra, supernova light curves, remnant maps, galactic abundance patterns, and planet formation models. Nuclear binding energies explain why fusion releases energy up to iron and not beyond in the same way. Spectroscopy identifies elements in stars and remnants. Isotope ratios in meteorites preserve early solar system conditions. Surveys of stars at different ages show chemical evolution. Observations of disks show dust and gas forming planetary systems. None of these alone proves the whole story. Together, they form a coherent chain that can be tested, revised, and expanded. There is a quiet discipline in that chain. Astronomers do not touch Cassiopeia A. They do not collect a vial of gas from the Crab Nebula. They cannot watch the sun's birth cloud form again. They rely on light, particles, rare samples, and mathematical models. The universe is generous with evidence, but not with convenience. A spectral line must be interpreted. A meteorite inclusion must be dated. A simulation must be compared against observation. A beautiful image must be reduced to physical conditions. This is how knowledge crosses distance, not by certainty arriving whole, but by evidence accumulating until a picture becomes difficult to deny. The phrase "dying stars create planets" and life can also be heard backward. Planets and life are evidence that earlier stars died. Earth itself is a kind of archive. Its rocks are made of elements that required stellar processing. Its core contains metals that could not have formed in the Big Bang. Its biosphere uses chemistry unavailable in a pristine universe. When you look at Earth from space, blue and white and brown against black, the planet does not visibly announce this ancestry. But the ancestry is there in every mineral, every ocean molecule, every living cell. A habitable planet is a late product of cosmic recycling. The word recycling is useful, but it should not make the process seem gentle. The material is not passed along smoothly from star to planet. It is heated to millions of degrees, compressed, ionized, shattered, shocked, cooled, frozen, melted, differentiated, eroded, subducted, dissolved, metabolized, and sometimes blasted back into space by impacts or winds. A carbon atom may spend time in interstellar gas, in a dust grain, in a planetesimal, in a carbonate rock, in volcanic carbon dioxide, in an ocean, in a microbe, in a shell, and back in rock again. The supernova is one dramatic step, but matter keeps moving after that. In the far future, the Sun will return some of its material to space through a gentler stellar death. It will not make a core collapse supernova, but it will enrich the interstellar medium with material altered by its own life. Earth may not survive in any recognizable form, and life on the planet will end long before the Sun becomes a white dwarf. But the atoms themselves will continue. Some may enter interstellar space. Some may remain locked in remnants. Some may be incorporated into future clouds if the galaxy's conditions allow. The cycle is not designed for life, but life can arise within it during windows of stability. Supernovae remind us that creation in the universe often comes from processes that are not safe for what already exists nearby. A shockwave can compress a cloud and help form stars, but it can also tear a cloud apart. Heavy elements can build planets, but radiation can strip atmospheres. Massive stars can enrich galaxies, but they live briefly and die violently. This is not contradiction. It is the nature of physical systems. The universe does not separate construction from destruction in the way human language does. The same event can be catastrophic locally and generative over astronomical time. A supernova remnant expands through space like a sentence that takes thousands of years to finish. At first, it is a blinding transient. Then it becomes a shell, a nebula, a source of X-rays and radio emission. Later it becomes faint, diffuse, difficult to distinguish from the surrounding medium. Its elements keep moving after its shape is gone. Eventually, no telescope can point to the original boundary and say where the supernova ends, yet the material remains part of the galaxy. Some of it may help form a star, whose planets will never know the name of the remnant that contributed to them. The Milky Way contains many known supernova remnants, but likely many more have faded or remain hidden. Radio surveys find shells, X-ray observatories find hot gas, gamma-ray observations trace high-energy processes, infrared telescopes reveal dust, optical images show filaments where shocks excite gas. Each catalogued remnant is a local example of a galaxy-wide process. In other galaxies, supernova remnants can be studied as populations, showing how stellar death interacts with different environments. In starburst galaxies, many supernovae can overlap, driving winds that push enriched gas out of the galactic disk. Some of the elements made by stars may leave their original galaxies entirely. This raises another uncertainty in the story of cosmic enrichment. Galaxies are not closed boxes. Gas falls in from the intergalactic medium. Gas flows out through winds powered by supernovae, radiation, and active galactic nuclei. Smaller galaxies can lose enriched material more easily because their gravity is weaker. Larger galaxies can retain more of it. When astronomers measure metallicity in galaxies of different masses and ages, they are seeing the combined effects of star formation, stellar death, inflow, outflow, and mergers. Supernovae create elements, but whether a galaxy keeps those elements depends on gravity and feedback across enormous scales. Somewhere between these scales sits a single rocky planet. It has no awareness of galactic winds or chemical evolution. It forms because local solids collide, heat, melt, and separate. Yet its existence depends on the galaxy having kept enough heavy elements long enough for them to enter the right cloud. This is why the story can move from Cassiopeia A to Earth without becoming fantasy. The connection is not emotional, first. It is material. The same periodic table appears in remnant spectra and planetary geology because atoms obey the same rules everywhere we can measure them. Consider calcium. In a supernova remnant, calcium can be detected through emission from hot, shocked material. In a meteorite, calcium can appear in ancient inclusions that formed at the beginning of the solar system. On Earth, calcium enters minerals, shells, teeth, bones, and cellular signaling. The uses are different because the environments are different. Hot plasma does one thing, a cooling disk does another, a living body does another. But the nucleus is the same kind of nucleus. The difference between cosmic debris and biology is not a difference in ingredients alone. It is organization, temperature, pressure, chemistry, and time. Silicon follows a similar path. Supernovae and massive stars help supply silicon to the interstellar medium. In the solar system, silicon combines with oxygen and metals to form silicate minerals. These minerals make up much of Earth's mantle and crust. They form rocks, sand, dust, and planetary interiors. Silicon also appears in interstellar dust grains and in the spectra of remnants. The same element is mapped by X-ray telescopes in a young remnant and held in your hand as a piece of quartz or basalt. The transformation from remnant to rock requires many stages, but the nuclear origin is part of the rock's history. Iron, silicon, oxygen, magnesium, sulfur, calcium, carbon, nitrogen, phosphorus, none of these makes life inevitable, but without them, Earth would not be Earth. A universe containing only hydrogen and helium could still have stars and gravity. It could still have galaxies and radiation. But it would lack the chemical diversity needed for rocky planets and complex molecules. The difference between a simple universe and a chemically rich one is written in the life cycles of stars. Supernovae are among the most important punctuation marks in that writing. They end individual stars and expand the chemical vocabulary of everything that comes after. The first time a massive star exploded in a young galaxy, it changed not only its surroundings, but the future possibilities of that region. The gas was no longer pristine. Heavy atoms existed where they had not existed before. Cooling pathways changed. Dust could begin to form. Later stars could have different masses. Later disks could contain solids. This would happen again and again, in galaxy after galaxy, across billions of years. By the time the Sun formed, the process was ancient. The solar system was not at the beginning of chemical creation. It was an inheritor of a long and violent accumulation. We should also avoid imagining that supernova material arrives neatly mixed in every cloud. Observations and models show that mixing can be incomplete. Some regions may be enriched by a nearby event more strongly than others. Isotopic anomalies in meteorites may preserve small-scale heterogeneity from the solar nebula. Precellar grains show that not every particle was homogenized before planet formation. This unevenness is valuable because it preserves information. If the galaxy mixed everything perfectly, many clues would be erased. Imperfect mixing makes the early solar system more complicated, but also more readable. In meteorite laboratories, scientists measure isotopes with precision unimaginable to early astronomers. They can compare ratios of oxygen isotopes, magnesium isotopes from aluminum-26 decay, nickel isotopes, chromium isotopes, and many others. These measurements test whether material came from supernovae, stellar winds, asymptotic giant branch stars, or other sources. The numbers can be difficult to interpret, and different models may compete. But the basic principle is powerful. Atoms carry nuclear histories. A rock that falls to Earth can become evidence for stars that lived before the Sun. This is one of the few ways humans physically touch the pre-solar universe. A telescope receives light. A detector receives particles. But a meteorite can be held, cut, polished, dissolved, and measured. It is a piece of early solar system material that arrived naturally. Inside some meteorites are grains older than Earth, older than the Sun, older than the disk that made the planets. They are not large, they are not visually spectacular without instruments, yet they survived a journey through interstellar space and planetary formation. Their existence makes the cosmic cycle tangible. Some presolar grains contain isotopic signatures associated with supernovae. Others point to red giant stars or other stellar environments. A single meteorite can contain grains from different sources, mixed into the solar nebula before the planets formed. This is not a clean inheritance from one parent star. It is more like an old archive assembled from many destroyed libraries, each page carrying a different ink. The analogy is imperfect, but the science is concrete. Isotopy ratios differ because nuclear reactions in different stars produce different patterns. The grain remembers the conditions in which it condensed. The phrase heavy elements can also be misleading because astronomers use metal to mean any element heavier than helium. Oxygen is a metal in astronomical language, even though it is not a metal in everyday chemistry. Carbon, nitrogen, neon, magnesium, silicon, sulfur, calcium, and iron all count as metals to an astronomer. This terminology reflects cosmic abundance rather than laboratory categories. Hydrogen and helium dominate ordinary matter in the universe. Everything else is a smaller but crucial fraction. Planets like Earth are built from that smaller fraction. Life depends on it. Supernovae help supply and redistribute it. The sun's metallicity tells us it formed from enriched gas, but it does not by itself identify every source. To reconstruct the history, scientists compare the sun with other stars, meteorites, galactic chemical evolution models, and observations of nearby star-forming regions. The sun is neither extremely metal-poor nor extremely metal-rich by local standards. It belongs to a galaxy that had already undergone billions of years of star formation. Its composition reflects many previous generations. The solar system's existence is therefore evidence of a mature chemical environment, one produced by repeated cycles of stellar birth and death. In the long view, galaxies are not just collections of stars. They are chemical engines. Gas enters. Stars form. Massive stars die quickly. Smaller stars return material slowly. White dwarfs detonate after delays. Neutron stars merge rarely but dramatically. Black holes may shape gas through accretion and jets. Supernovae stir, heat, enrich, and sometimes expel matter. The galaxy changes composition over time. Rocky planets become more likely in some regions and epochs. The universe becomes capable of building structures that the first stars could not have built around them. This does not mean the early universe was lifeless everywhere by definition, because the exact timing of the first possible habitable planets remains uncertain. But it does mean complex chemistry required enrichment, and enrichment required stars to process and distribute elements. Supernovae were among the fastest ways to do that because massive stars die quickly. They can enrich their surroundings within a few million years of forming. Type 1a supernovae add important material later, especially iron group elements. Different sources operate on different clocks. Planetary possibility grows out of those clocks overlapping. In a young star cluster, the most massive stars are the first to leave the main sequence. Their ultraviolet radiation ionizes gas into glowing regions. Their winds carve cavities. Their deaths may produce supernova remnants, while lower mass siblings continue shining normally. The cluster then disperses under internal motion and external gravity. Some stars may carry disks. Some disks may already be forming planets. The environment can be harsh. Radiation can erode disks near massive stars, but enrichment and compression may also occur nearby. The birthplace of planets can be both nurturing and destructive, depending on distance and timing. A planet forming too close to a future supernova could lose its disk material or later face radiation hazards. A planet forming from gas, never enriched by massive stars, might lack enough solids. The useful zone is not a simple distance. It is a history. How close were the massive stars? When did they explode? How dense was the cloud? How quickly did the disk form? How much material was injected, and how well did it mix? These are not questions with universal answers. They are questions from models, observations of star-forming regions, and isotopic evidence from old solids. Earth sits at the end of one successful history, though successful only from the narrow perspective of life here. The planet formed, differentiated, cooled, retained enough water, developed stable surface environments, and passed through impacts and atmospheric transformations. Supernovae did not arrange these details. But they helped make the material possible. Their contribution is older than geology. It belongs to the inventory from which geology began. Before there were oceans, there had to be oxygen. Before there were continents, there had to be silicon, aluminum, magnesium, and iron. Before there were cells, there had to be carbon, nitrogen, phosphorus, sulfur, and metals for enzymes. The question of how dying stars create life is therefore not a biological question at first. It is a question about whether the universe can make the ingredients for biology and put them in the right environments. Supernovae answer part of it. They make and eject heavy elements. They help stir galaxies. They leave remnants whose spectra show the materials we later find in planets. Biology begins much later, under cooler and gentler conditions, in liquids and minerals and membranes, not in the blast. The supernova is not where life begins. It is where some of life's required atoms enter the wider universe. The atoms then lose any memory of being dramatic. An oxygen atom in a molecule of water does not behave like a remnant. An iron atom in a protein does not glow in X-rays. A phosphorus atom in DNA does not announce the stellar burning that made it possible. Chemistry depends on local bonds, charges, temperatures, and environments. Nuclear history sets the inventory, but chemical history sets the behavior. This separation is important. The atom's origin is cosmic. Its role in life is local. A planet turns stellar ash into oceans and cells not by remembering stars, but by organizing matter under planetary conditions. Scientific language sometimes calls this stellar ash, but actual ash is the residue of chemical combustion. Supernova ejecta are nuclear ash, the products of fusion and explosive burning, along with material that was not fully processed. The distinction matters because nuclear reactions change nuclei themselves, while ordinary fire changes molecules. Stars do not burn like wood. They fuse atomic nuclei under extreme temperature and pressure. Their ash is not soot. It is helium, carbon, oxygen, silicon, iron, and many other nuclei formed through nuclear pathways. When those nuclei later become molecules in a planet's atmosphere or ocean, they have entered a completely different regime of physics. There is a deep continuity here, but not a simple one. Gravity compresses gas until stars ignite. Nuclear fusion resists gravity for a time. Fusion builds heavier nuclei. Gravity eventually wins in massive cores. Collapse triggers explosion. Explosion releases material. Gravity later gathers enriched clouds. Disks flatten under rotation. Dust grows into planets. Planetary gravity holds atmospheres and oceans. Chemistry becomes complex. Life emerges, if it does, through pathways still being investigated. The same force that killed the star also helped build the planet. Gravity is present at nearly every stage, changing its expression as the scale changes. Radiation also changes roles. In a massive star, radiation pressure helps support outer layers. In a supernova, radiation floods the expanding ejecta and powers the visible display. In a remnant, radiation reveals hot gas and energetic particles. In a molecular cloud, radiation can heat or ionize gas and influence collapse. In a protoplanetary disk, radiation from the young star shapes chemistry and evaporation. On a planet, radiation can damage molecules or power photosynthesis, depending on wavelength and context. The same broad category of physical process can destroy, reveal, regulate, or sustain, depending on environment. This is why the title should not be read as a claim that supernovae are benevolent. They are not benevolent. They are not hostile either. They are physical events. They follow from stellar mass, nuclear physics, and gravity. Their consequences can be violent, useful, dangerous, or essential depending on the timescale and location. For a planet too near, a supernova could be a crisis. For a molecular cloud millions of years later, it may be part of the enrichment history. For a biologist studying DNA, its relevance is hidden in the availability of phosphorus and metals. The same event can appear different from different distances in time. A telescope image collapses those distances into one frame. Cassiopeia A appears as a remnant now, but the star that exploded was born long before the explosion in a cloud that had its own ancestors. Its ejecta will continue long after the remnant fades. The image is a middle chapter, not the whole book. It shows material between star and galaxy, between core and cloud, between death and future formation. That is why it is such a powerful object for this topic. It does not merely show that stars explode, it shows that the interior of a star can become interstellar matter. The remnant's expansion can be measured by comparing images taken years apart. Filaments shift outward. Proper motions give velocities when distance is known or estimated. Spectral shifts add line of sight motion. Together, these measurements can reconstruct an expansion history and estimate an explosion date. This is how astronomers connect remnants to historical events or infer ages when no human record exists. The method is not perfect because remnants slow as they encounter surrounding material, and different knots move differently. But repeated observation turns a static-looking nebula into a dynamic system. In a processed image, the filaments may look frozen. In reality, they are racing outward. Human lifetimes are short, so the motion seems slow, unless measured with precision. A knot that barely shifts on a detector may still be moving at thousands of kilometers per second. Astronomy often lives in this mismatch. The universe moves violently, but distance and scale make the violence appear still. A supernova remnant can be both fast and visually patient. It changes enough for instruments to detect, but not enough for casual looking to understand. The same mismatch appears in planet formation. A protoplanetary disk may evolve over millions of years, but individual collisions happen quickly. A planet may take tens of millions of years to assemble, but a giant impact can reshape it in hours. Life may take hundreds of millions of years to transform a surface, while a mutation occurs in a molecule. The supernova to life chain is not one timescale, it is many timescales nested together. Stellar burning, explosive seconds, remnant thousands of years, interstellar mixing millions of years, planetary formation millions more, biological evolution billions. Understanding the chain means changing clocks repeatedly without losing the physical connection. Deep time is sometimes described as unimaginable, but science does not require us to imagine it all at once. It gives markers. A massive star may live for only a few million years. The Sun has lived for about 4.6 billion. The Milky Way has been forming stars for more than 10 billion. The universe is about 13.8 billion years old. Meteorites date the beginning of the solar system. Supernova remnants can be centuries or thousands of years old. Each number anchors a different part of the story. Together, they show that life on Earth is late enough to inherit many stellar generations, but early enough that the galaxy is still actively forming stars. The galaxy will not keep forming stars at the same rate forever. Gas is consumed, expelled, heated, and redistributed. Star formation may decline over cosmic time. New supernovae will continue as long as massive stars form and white dwarf systems reach detonation conditions. But the overall cosmic star formation rate peaked billions of years ago and has declined since. We live after that peak, in a universe still active but older than its most intense star-forming era. The chemical enrichment that made Earth possible happened within this broader cosmic history during a period when galaxies had already built substantial heavy element inventories. Dark matter and dark energy are not central actors in supernova nucleosynthesis, but they shape the larger stage. Dark matter helps galaxies form and hold together gravitationally, influencing where gas collects and where stars form. Dark energy describes the observed acceleration of cosmic expansion affecting the largest-scale future of galaxies and clusters. Type 1a supernovae helped reveal that acceleration. In this indirect way, supernovae connect local stellar death to cosmology. They make elements in galaxies, and their standardized light helps measure the expansion of the universe. The same class of events informs both chemistry and cosmic geometry. There is a quiet elegance in that. A white dwarf dies in a distant galaxy, and its light becomes a ruler for cosmic distance. A massive star dies in the Milky Way, and its debris becomes a source of oxygen and silicon. A remnant glows in X-rays, and its spectral lines become a map of buried stellar layers. A meteorite grain falls to Earth, and its isotopes become a trace of a star older than the Sun. None of these alone contains the whole story. Together they make the universe less separate from the world under our feet. If you were to stand beside a radio dish at night while it tracked a supernova remnant, nothing about the scene would look violent. The dish would move slowly. The sky would be cold and mostly dark. The signal would be weak, processed through receivers and stored as data. Yet the object being measured might be a shock front accelerating electrons in a magnetic field, thousands of light years away. Astronomy often looks calm at the human end because the violence is remote. The instruments do not dramatize it. They translate it into voltages, spectra, images, and tables. X-ray telescopes must operate above Earth's atmosphere because the atmosphere blocks most cosmic X-rays. This is fortunate for life, but inconvenient for astronomy. Observatories such as Chandra, XM Mean Newton, and X-RISM study hot plasma, compact objects, and high-energy processes that ground-based optical telescopes cannot see directly. Infrared observatories such as Webb reveal dust and cooler material. Optical telescopes show ionized gas and starlight. Radio telescopes trace synchrotron emission, molecules, and cold gas. A supernova remnant is therefore not one object in one kind of light. It is a physical system sampled by many instruments, each with blind spots. When those views are combined, the story becomes richer. X-rays may show freshly synthesized elements heated by shocks. Infrared may show dust and molecules. Optical lines may trace slower or denser filaments. Radio may show magnetic fields and relativistic particles. Gamma rays may point to radioactive decay or cosmic ray interactions. The same remnant can look like a shell, a web, a ring, or a patch of knots depending on wavelength. The difference is not inconsistency, it is stratification by physics. A human eye wants a single appearance. The universe offers multiple physical states at once. That complexity is why supernova yields are not measured by simply looking at a remnant and adding up colors. Astronomers need plasma models, distance estimates, temperature measurements, ionization states, densities, and assumptions about geometry. Some material may be too cool, too hot, too faint, or hidden behind absorption. Some has mixed with swept-up interstellar gas. Some has not yet been hit by a reverse shock and therefore does not emit strongly. Element masses in remnants are estimates, often revised as new data arrives. The broad picture is secure, but the details require caution. Even with those uncertainties, the image of a supernova as a chemical dispersal event remains one of the most powerful results in astronomy. It means the universe has a memory carried in matter. Stars do not simply shine and vanish. They alter the composition of space. They leave behind atoms that later become part of other stars, planets, and perhaps living systems. A galaxy is not chemically static. It matures. It becomes enriched. It accumulates the consequences of its own luminous population. Supernovae are among the most dramatic ways that accumulation happens. In the periodic table, iron sits near the peak of nuclear binding energy, which is why it marks a turning point for stellar fusion. Elements lighter than iron can release energy through fusion under appropriate conditions. Elements much heavier than iron generally require processes such as neutron capture. Slow neutron capture can occur in aging stars over long times, while rapid neutron capture requires environments with intense neutron fluxes, such as neutron star mergers, and perhaps some rare supernova-related events. This is why the origin of gold is not the same simple story as the origin of oxygen. Both are cosmic, but their factories differ. The distinction does not weaken the connection between supernovae and life. Most of life's mass is built from hydrogen, oxygen, carbon, nitrogen, phosphorus, sulfur, calcium, and trace metals. Many of these are produced or distributed by massive stars and their deaths, along with other stellar sources. The elements that make a rocky planet habitable are not all rare jewels. Oxygen and silicon are common in Earth's crust. Iron is abundant in Earth's core. Carbon is chemically flexible. The essential point is not that supernovae make every exotic element. It is that stellar evolution makes a universe where chemical complexity can exist at all. A child looking at a star sees a point of light. A spectrograph sees absorption lines. A stellar evolution model sees mass, composition, and future fate. A supernova survey sees a possible transient. A planet formation model sees a source of enrichment. A biochemist sees, much later, the elements that will become metabolism. The same star belongs to all these perspectives because it is a physical object in a connected universe. Its life is not only its own. If it is massive enough, its death changes the material available to worlds that form long after it is gone. The most massive stars may also collapse directly into black holes, especially depending on mass and metallicity. In such cases, the visible supernova may be weak or absent, and less material may be ejected than in a successful explosion. Pair instability supernovae, theorized and observed in candidate events, may completely disrupt extremely massive stars under certain conditions, leaving no remnant and producing distinctive yields. Electron capture supernovae may occur in a narrower mass range involving oxygen-neon magnesium cores. The taxonomy is still being refined. Stellar death is not one staircase. It is a branching set of outcomes shaped by initial mass, composition, rotation, and companions. Binary interaction may be especially important because many massive stars have companions. A companion can strip hydrogen, spin up a star, transfer mass, or merge. It can change what the star looks like when it explodes and what kind of remnant it leaves. For Type 1a supernovae, binarity is central because white dwarfs need a path to runaway burning, whether through accretion, merger, or surface detonation. This means a supernova is often not the death of an isolated star, but the final result of a relationship. The companion may survive, be destroyed, or become part of the explosion pathway. The universe builds complexity through interaction. Stars form in clusters, not in loneliness most of the time. Massive stars sculpt clouds before they die. Binaries exchange mass. Supernova shocks cross older wind bubbles. Ejecta mix with gas enriched by previous stars. Planet-forming disks inherit a blend of sources. Worlds collide and exchange material. Life evolves through networks of chemistry and environment. A supernova is dramatic because it is sudden, but it belongs to this broader pattern of systems influencing systems. Nothing in the chain is truly isolated. Observations of young remnants can test explosion models directly. If models predict certain element layers should be inside and observations find them outside, then mixing or asymmetry must be included. If a model produces too much nickel, the light curve may be too bright. If it produces too little, the tail fades incorrectly. If the predicted remnant shape is smooth, but real remnants are clumpy, turbulence must be stronger. This back and forth is why supernova science improves. The sky provides examples. Models try to reproduce them. Failures are not embarrassing if they reveal missing physics. There is patience in that process. A remnant is observed again. A spectrum is recalibrated. A model is rerun with different rotation. A dust estimate is revised. A new telescope opens a wavelength that was previously blurred or inaccessible. The story changes slightly, not because the universe changed, but because measurement improved. Scientific understanding of supernovae has not arrived all at once. It has been assembled across centuries, from guest stars in historical records to neutrino detections, space telescopes, computer simulations, and meteorite isotope laboratories. The next galactic supernova will test that entire structure. It may happen behind dust, visible only in infrared and radio at first. It may be bright enough to transform the night sky. It may produce a clear neutrino burst. It may leave a neutron star detectable almost immediately, or hide one for decades. It may match models well, or expose something missing. Astronomers prepare because the opportunity is rare on human timescales. The Milky Way has many stars capable of exploding someday, but someday is not a schedule. The universe gives these events when stellar interiors reach their limits, not when observers are ready. Until then, scientists study supernovae in other galaxies and remnants in our own. They build surveys, maintain archives, improve detectors, and refine simulations. Each distant transient adds statistics. Each nearby remnant adds detail. Each meteorite measurement adds a clue about the solar system's inheritance. Each observation of a protoplanetary disk shows what enriched material can become. The title asks how dying stars create planets and life, but the answer is spread across disciplines. Stellar astrophysics, nuclear physics, galactic evolution, cosmochemistry, planetary science, and biology all meet in the chain. The chain can be summarized, but not reduced too far. The Big Bang made mostly hydrogen and helium. Stars formed from that gas. Massive stars fused lighter nuclei into heavier ones and ended in supernovae. White dwarfs in binary systems sometimes detonated as Type Ia supernovae. These explosions and other stellar deaths enriched interstellar gas. Enriched clouds formed new stars and disks. Dust and ice in disks assembled into planets. Some rocky planets developed environments where chemistry could become complex. On Earth, that chemistry became life. Every sentence in that summary hides details, but the direction is supported by evidence from many independent lines. What makes the story remarkable is not that it is mystical, but that it is physical. No part requires the atoms to know where they are going. Oxygen does not seek oceans. Iron does not seek blood. Silicon does not seek continents. Carbon does not seek cells. Gravity gathers. Fusion builds. Collapse ejects. Clouds mix. Disks condense. Chemistry explores what bonds allow. Life, once it appears, uses what the planet provides. Meaning enters later, through minds that evolved from the same material and learned to look back at the remnants. In that sense, a supernova remnant is not only an object far away, it is a clue to why objects nearby exist at all. The rock, the ocean, the atmosphere, and the body are not separate from stellar history. They are cooled, rearranged, localized forms of matter that once belonged to larger cosmic cycles. The remnant shows the violent stage. Earth shows one quiet result. Between them lies the long work of a galaxy, mixing and reshaping what stars leave behind. The evidence in Cassiopeia A remains especially direct because the remnant displays elements in space. Chandra maps X-ray emission from different ions. Webb resolves infrared knots and dust structures. Those features can be compared with the expected layers of a massive star. The remnant's neutron star, its ejecta, its shock waves, and its chemical maps all point to a core collapse origin. It is not the source of Earth's atoms specifically, but it is an example of the process that contributed to the kind of material Earth needed. It is a nearby demonstration of galactic recycling in progress. If a future cloud forms from gas that includes material like this, the atoms will not remain marked with a visible label. They will mix with older gas, with dust from other stars, with materials swept from the interstellar medium. The future star may form quietly, hidden in infrared dark dust. Its disk may appear as a faint oval in a telescope image. Planets may grow unseen inside it. Millions of years later, if one of those planets becomes rocky and temperate, no observer standing on its surface would see Cassiopeia A. The remnant would be gone or transformed. The inheritance would be chemical. This is why evidence matters more than imagination in this story. It would be easy to picture a glowing stream from supernova to planet, but nature is not that cinematic. The real chain is more fragmented and more interesting. It includes failed mixing, destroyed dust, delayed cooling, turbulent clouds, partial collapse, disk chemistry, chaotic impacts, and uncertain biological origins. The connection survives all that difficulty because atoms persist. They can be heated, ionized, locked into minerals, dissolved in oceans, or built into proteins, but the nuclei remain part of the same cosmic accounting. A supernova is one of the universe's reminders that stability is temporary for stars above a certain mass. Their brilliance is not sustainable forever. The same gravity that makes them shine eventually forces their cores into collapse or their remnants into detonation. But temporary does not mean meaningless in physical terms. A massive star can live only a few million years and still change its galaxy for billions. Its light shapes clouds while it lives. Its winds enrich space before it dies. Its explosion distributes the products of its core. Its remnant accelerates particles and stirs gas. Its material continues after the star is gone. The planets created from such material are also temporary. Rocky worlds cool, collide, erode, lose atmospheres, freeze, overheat, or fall into stars. Life, where it appears, occupies a narrower window still. But matter outlasts forms. The atoms in a living organism will not remain in that organism. They will move into air, water, rock, sediment, other organisms, or eventually, over astronomical time, perhaps back into space. The supernova to life story is therefore not a straight line ending with us. It is a cycle with temporary arrangements. We are one arrangement that became able to ask where its ingredients came from. When astronomers say we are made of star stuff, the phrase is only useful if it leads back to the measurements. X-ray lines in remnants. Spectra of stars. Isotopes in meteorites. Abundances in galaxies. Nuclear reaction rates in laboratories and simulations. Without those, the phrase becomes decoration. With them, it becomes a compressed statement of evidence. The iron in hemoglobin, the calcium in bone, the oxygen in water, and the silicon in rock all belong to a cosmic chemical history that can be studied, not merely admired. The admiration still has a place. A telescope image of a remnant can be beautiful before it is understood. A meteorite can feel ancient before its isotopes are measured. A dark sky can inspire questions before any equation is written. But the beauty deepens when the evidence is allowed to remain evidence. The colors in Cassiopeia A are not just colors, they are elements. The shell is not just a shell, it is expanding plasma. The filaments are not just delicate shapes, they are shocked gas, dust, and heavy atoms moving through space. Somewhere, in a galaxy too faint to see without long exposure, another massive star is approaching its final burning stages. Its surface may look ordinary to a distant observer. Its core may be days from collapse, or centuries, or thousands of years. Around it, perhaps, other stars in its birth region are still young. Some may have disks. Some may one day host planets. When the massive star dies, its light will become a transient in a survey. Its neutrinos will vanish into space. Its ejecta will begin the long work of dispersal. Most of the universe will not notice. The local gas will. The future material from that star may never enter a living world. It may remain in hot gas, fall into another star, be locked into a giant planet, or escape into intergalactic space. But across countless events, enough material enters the right places. This is how probability replaces destiny. No single supernova has to create life. Many stellar deaths across billions of years create the conditions under which planets and life become possible somewhere. Earth is one known result. It is not proof that the chain always leads to biology, but it proves that the chain can lead to biology at least once. The search for life beyond Earth therefore depends partly on supernova history. A potentially habitable exoplanet must orbit a star in a chemically enriched environment. It must have access to heavy elements and volatiles. Its system must have formed from a disk with enough solids. Its star must be stable enough for long-term surface conditions, unless life follows a different path. Its galactic environment must not be too hostile too often. Supernovae influence several of these factors. They enrich the gas, but nearby explosions can also threaten atmospheres. Habitability is not only a distance from a star. It is a history within a galaxy. This is why ideas like a galactic habitable zone are debated rather than settled. Regions too close to a galactic center may have higher radiation, dynamical disturbances, or supernova rates, but also more heavy elements. Outer regions may be quieter but less enriched. Over time, these patterns change as galaxies evolve. The Milky Way is not uniform, and neither are other galaxies. A planet's chance of becoming habitable may depend on where and when it forms, not just on its orbit. Supernovae are part of that geography of risk and enrichment. The universe that can make life is therefore not the gentlest universe imaginable. It is a universe with violent stellar deaths, galaxy mergers, shockwaves, radiation, and long periods of darkness between stars. It is also a universe with cooling clouds, stable orbits, molecular chemistry, rocky surfaces, and oceans. The same cosmic history contains both. Supernovae sit at the boundary between destruction and preparation. They are endings for stars and beginnings for material. They do not care which role we emphasize. The evidence shows both at once. When the remnant expands, it carries kinetic energy into the interstellar medium. When it cools, atoms can recombine. When dust forms or survives, solids enter the gas. When a later cloud collapses, that material can be incorporated into a new star system. This is not speculation in its broad outline. It is supported by observed remnants, enriched stars, meteorites, and planet-forming disks. The uncertainties are in the details: exact yields, mixing efficiency, dust survival, source contributions, and local histories. Science often works this way. The main structure can be strong while many internal beams are still being measured. In the end, the most important image may not be the explosion itself. It may be the remnant after the spectacle, when the light has faded enough for the structure to be studied. Or the molecular cloud long afterward, cold and dark, carrying a chemical inheritance. Or the disk around a young star, where dust grains begin to gather. Or the meteorite in a laboratory, quiet under bright lights, preserving grains older than the sun. These scenes are not as dramatic as a star tearing itself apart, but they are where the consequences become visible. A dying star creates planets and life by refusing to keep its interior to itself. Through collapse, explosion, wind, detonation, and dispersal, stellar material is returned to space. The galaxy receives it imperfectly. Time mixes it unevenly. Gravity gathers some of it again. Chemistry builds with what is available. A planet forms from the leftovers of a star-forming disk, and if conditions allow, the atoms that once moved through stellar interiors become part of oceans, rocks, air, and living tissue. The path is long enough that no single object contains it. We understand it by connecting many kinds of evidence. The periodic table in a classroom looks stable, arranged in rows and columns, but in astronomy it is also a history of events. Hydrogen and helium point back to the early universe. Carbon and oxygen point to stellar interiors. Silicon, sulfur, calcium, and iron point strongly to massive star burning and explosive release. Iron group elements also point to Type 1a supernovae over long galactic times. Some of the heaviest nuclei point to neutron-rich catastrophes, such as neutron star mergers. The table becomes less like a list and more like a map of origins. Every element has a pathway, and many pathways pass through dying stars. When astronomers measure a star's composition, they are reading that map in starlight. A star's atmosphere absorbs and emits light at wavelengths set by the atoms inside it. Those lines can reveal iron, oxygen, magnesium, carbon, sodium, calcium, and many other elements. The star may be too distant to resolve as anything but a point, yet its spectrum contains chemistry. If it is metal-poor, it may have formed early or from less enriched gas. If it is metal-rich, it likely formed from gas processed by many previous generations. A spectrum is not just light split into color. It is a chemical memory of the cloud that made the star. There are stars in the Milky Way halo with extremely low metal content, and they are valuable because they preserve information about early enrichment. Some may carry the imprint of only a few earlier supernovae. Their abundance patterns can test models of the first massive stars and their explosions. But even here, interpretation is careful. The star observed today did not necessarily form in the same region of the galaxy where it now moves. It may have been accreted from a smaller galaxy. Its surface may have been altered by binary interaction. The evidence is powerful, but it is still evidence in a dynamic galaxy. Planetary science adds another layer. Earth differentiated because it became hot enough for materials to separate by density. Iron and nickel moved inward to form the core. Lighter silicates formed mantle and crust. Volatile compounds entered atmosphere and ocean through degassing, impacts, and chemical exchange. Radioactive isotopes provided heat. Plate tectonics, if sustained in part by internal heat and water, recycled carbon and shaped climate over long times. None of these processes is a supernova process directly. But they all require the heavy element inventory that stellar evolution and supernovae made available before Earth existed. A granite cliff, a basalt plain, a band of iron-rich rock, a limestone shell, and a living leaf all look unrelated at human scale. One is geology, one is mineral deposit, one is biology. But each depends on elements that were not born on Earth. The cliff needs silicon, oxygen, aluminum, potassium, and trace elements. The basalt needs iron, magnesium, silicon, and oxygen. The shell needs calcium, carbon, and oxygen. The leaf needs carbon, hydrogen, oxygen, nitrogen, magnesium, phosphorus, sulfur, and metals in tiny amounts. Supernovae are not visible in these objects, but their chemical inheritance is present. The solar system also contains giant planets, and they tell a related story. Jupiter and Saturn are mostly hydrogen and helium, but they contain heavy elements too, in cores, atmospheres, and enriched interiors. Uranus and Neptune contain larger fractions of ices and heavier material. Moons, rings, asteroids, and comets preserve different mixtures of rock, metal, organic compounds, and frozen volatiles. A chemically enriched disk does not make only Earth like planets. It makes a whole architecture of bodies, each sorted by temperature, gravity, formation location, and later collisions. Supernova enrichment feeds the disk, but disk physics decides how the ingredients are divided. Comets may carry ices from the cold outer solar system, including water, carbon monoxide, carbon dioxide, methane, ammonia, and organic molecules. Asteroids may preserve rock and metal from the inner disk. Some meteorites record melting and differentiation on small worlds that were later shattered. These small bodies are not leftovers in the sense of being unimportant. They are records of planetary formation that escaped full transformation. In them, the cosmic chain becomes granular. A chondrule, a metal grain, a calcium-aluminum inclusion, or a prissolar grain can hold evidence of heat, shock, condensation, and nucleosynthesis on scales far smaller than a planet. The origin of Earth's water is still studied, and it should not be assigned casually to any single source. Some came from material incorporated during formation. Some may have been delivered by asteroids or comets, with isotopic ratios helping test possibilities. Supernovae did not make water directly for Earth in the form oceans now take. They helped supply oxygen and influenced the chemistry of the cloud that became the solar system. Water then formed and moved through disk chemistry, mineral hydration, impacts, degassing, and atmospheric evolution. The ocean is cosmic in ingredients, but planetary in assembly. The same caution applies to organic molecules. Carbon-bearing compounds are found in interstellar clouds, protoplanetary disks, comets, meteorites, and planetary atmospheres. Some can form on dust grains under cold conditions. Some form through ultraviolet chemistry. Some form in warm planetary environments. Supernovae contribute carbon and help shape the interstellar medium, but they are not the only source of organic chemistry. What they provide is part of the elemental foundation and part of the environmental history that allows chemically rich clouds and disks to exist. In a radio spectrum of a molecular cloud, a narrow line from carbon monoxide can trace cold gas that may one day form stars. In an infrared spectrum of a disk, features from silicates can reveal dust grains like those that build rocky bodies. In an X-ray spectrum of a remnant, silicon and iron lines show the aftermath of stellar burning. These observations are rarely shown together, but they belong together. They are different stages of the same matter cycle: hot ejecta, mixed gas, cold cloud, dusty disk, solid body. Astronomy becomes a way of watching matter change phases across millions of years. The violence of a supernova can also erase evidence. A nearby explosion may strip gas from a forming system, destroy fragile molecules, or flood a region with radiation. A shock can alter isotopes, heat dust, and reset chemical pathways. Later, planetary melting and differentiation erase much of the original disk record. Earth's active geology has destroyed most of its earliest surface history. This is why meteorites are so important. They preserve what planets often do not. They keep pieces of the early record that Earth itself recycled beyond recognition. There is humility in that dependence on fragments. To understand how dying stars helped make planets and life, scientists use remnants thousands of light years away, stars too distant to visit, clouds too cold to see invisible light, disks around young stars, and stones that fall from space. None gives the whole chain. Each gives a piece. The story becomes trustworthy, not because every piece is complete, but because the pieces point toward the same broad conclusion. The universe became chemically rich through stars, and supernovae are among the events that made that richness available. A future civilization around another star, if one exists, might look at its own rocks and ask the same question. Its planet might have a different mix of elements, a different ocean history, a different atmosphere, a different biology if biology emerged there at all. But if it is a rocky world in a mature galaxy, it too would owe its solidity to earlier stellar generations. Its scientists might map remnants in their sky, measure isotopes in their meteorites, and discover that their local world is connected to stellar deaths they never witnessed. The conclusion would not be human-centered. It would be galactic. Even the silence between nearby stars is not chemically empty. It contains sparse atoms, dust grains, magnetic fields, and traces of older events moving too slowly and thinly for human senses, but not too thinly for astronomy to measure across enough distance. Cassiopeia A is still expanding. Its knots of oxygen, silicon, sulfur, calcium, and iron continue outward, shaped by shocks and magnetic fields. SN 1987A is still changing as its blast wave interacts with rings of older material. The Crab pulsar is still spinning down, feeding energy into its nebula. Across the Milky Way, other remnants are fading into gas that may someday cool again. And in laboratories on Earth, meteorites still hold grains from stars that died before the Sun existed. The story is not finished because the material is not finished. It is still moving. Long after a supernova's first light has vanished from the sky, the physical consequences remain. The remnant thins. The shock weakens. The atoms disperse. Some drift through the galaxy for ages. Some enter clouds. Some become dust in the cold. Some fall into new disks around young stars. A small fraction may become part of rocky worlds, and a smaller fraction still may enter the chemistry of life. This is how a dying star can help create planets and living things, not by miracle, not by intention, and not in a single instant, but through matter, energy, gravity, chemistry, and time.